Hello everyone, welcome to the video solution for past paper. This is Edexcel IAL Physics Unit 5, uh, June 2018, the second video of the series. So let's start. Question number 16. In an incandescent lamp, a metal filament is heated to a high temperature so that it emits light. The filament is enclosed in a glass bulb filled with an inert gas. Okay, a filament lamp glass bulb inert gas. Okay, in one type of lamp the filament is heated to a temperature of 2630 Kelvin. Show that lambda max wavelength of the maximum radiation of peak power emission from the filament is approximately 110 to the power minus 6 meter. So we are given temperature, we need to find lambda max. Clearly it is nothing but Wayne's law. So of Wayne's law of black body radiation, in which you know that lambda max into temperature is equal to constant, some constant, and constant is given in your formula sheet. So you can use the temperature, you can find lambda max using the constant given in your formula sheet. So you can find lambda max into the constant. The value of the constant is 2.898 10 to the power minus 3 meter Kelvin divided by temperature, and the temperature is 2630. So lambda max would be equal to 0.0011 into 10 to the power minus 3 meter, and if you shift this decimal here it will be 10 to the power minus 3 and minus 3, so 1.1 10 to the power minus 6 meter. This is the wavelength of maximum radiation. Suggest using the value of lambda max why the lamp is inefficient as light source. Indeed, if you see the lambda max calculated, the wavelength of maximum radiation, so maximum radiation will be, will have a wavelength of order 10 to the power minus 6. And if you see electromagnetic spectrum, so this order 10 to the power minus 6 belongs to infrared region. That means most of the light of this bulb consists of infrared radiation, and very little amount of light will be visible. So that's why it is inefficient. The pressure of the inert gas inside the bulb is 58.5 kilopascal at a temperature of 18 degrees Celsius. When the lamp is on, the temperature of gas is 165 degrees Celsius. Calculate the pressure of the gas when the lamp is on. Clearly, you know that in the bulb, volume stays the same, number of particles stays the same. So if you see, you have a formula PV equal to NKT, and from here pressure is directly proportional to the temperature, because V, N and K, they are constant, they are not changing when the bulb is turning on. So from this relation you can say that P1 upon T1 is equal to P2 upon T2. So you can figure out second pressure of pressure of second condition. So P2 would be equal to P1 T2 divided by T1. So P1 is initial pressure 58.5 kilopascal, so 10 to the power 3 into T2. T2 is final temperature, which is 165. Don't forget to change these temperature into Kelvin. So 438 divided by 291. So this temperature should be Kelvin after plus 273 and plus 273. When you solve this, so P2 would be equal to 8.81 into 10 to the power 4 Pascal. This is the pressure. Or if you wish, you can convert this into kilo after shifting this decimal here. So 10 to the power 3. So it will be close. So 88.1 kilopascal. A student uses a lamp to estimate the luminosity L of the sun. She places a small drop of cooking oil at the center of a sheet of card and spreads it out to form a small circle. She holds the card between the lamp and the sun. Light from the sun passes through the oil spot and the light from the lamp is scattered off the card. So this is the card. This is the card, and light from the sun passing through the oil spot. So if the sunlight is passing through the oil, so it looks like this, and this outer region is is shown due to scattering light from the lamp. Okay, this is a scenario, this is a situation. Sun, and this card is here, lamp, and at this position, suppose this is a situation. So she adjusts the position of the card until the brightness of the scattered light is the same as brightness of the light passing through the card. She measures the distance between the card and the lamp. So what she is doing, she is moving card either towards the lamp or away from the lamp, adjusting the distance so that both the brightness looks same. Once she got the position where both the brightness are same, so we need to calculate a value of L. L is the luminosity of the sun, remember, because the purpose is where she wishes to find the luminosity L of the sun. So calculate the value of L. Distance from the earth to the sun is 150 10 to the power 11 meter. Distance from the card of the lamp is 0.125. Power of the lamp is 200 watts. Okay, so we have to find luminosity of the sun, L, and for this purpose we have a relation of luminosity and the brightness, so which is brightness F is equal to, or intensity also, so that luminosity divided by 4 pi d square. So we can say that we can find the luminosity if we have F, brightness, 4 pi d square. We have distance of the sun, which is ds. Luminosity of the sun can be found if we have Fs, but we don't have Fs. So first we need to figure out Fs, brightness of the sun. And how do we do that? We are going to figure out brightness of the lamp. This is luminosity of the lamp, and we have distance of the lamp, and this is the distance of the sun. So using these two, we can figure out brightness of the lamp. And this brightness, because they are saying that she measures, she adjusts the distance, so the brightness of scattered light is the same as brightness of the sunlight. That's why FL is equal to Fs. So we can use this to figure out luminosity of the sun. So let's figure out FL. So FL would be equal to 200 divided by 4 pi, which is d square, and d square is 0.125 whole square. So once you solve this, so luminosity would be brightness FL would be equal to 1.02 into 10 to the power 3 watt meter minus 2. Now we can say luminosity of the sun would be equal to Fs, and Fs is as same as FL, which is 1.02 into 10 to the power 3 into 4 into value of pi 3.14 into ds, and ds is 1.5 times power 11, so times 1.5 into 10 to the power 11 whole square, and then luminosity of the sun would be equal to 2.88 into 10 to the power 26 watt. That's how you can figure out. Suggest reason why this method uh, is likely to result in poor estimate of sun's luminosity. Indeed, number one is it is really difficult to figure out the position or the point where the brightness of any on the card is same. So it is really difficult to detect whether the brightness on the card are same. That means FL is equal to FL, FS is equal to same or not. And moreover, if you see the distance of the lamp, which is 0.125, which is quite low value, a small value of the distance of the card to the lamp, so we have a large uncertainty in the distance, so that's why we have a poor estimation. It's not that good. The graph shows how the binding energy per nucleon varies with nucleon number for a range of nuclides. State what is meant by binding energy of nucleon or binding energy of nucleus. So you know that the binding energy is all about energy that bounds the nucleon together. So we have nucleons, like suppose these are the protons, and we have a neutrons, and they bound together something like this, you can imagine. So in order to break, in order to separate these nucleon, we need to give some energy. So energy given to the nucleon in order to separate. So per nucleon, this is called binding energy. So we need to just separate them, break them, something like this. So use the graph to explain why nuclear fission is only possible as an energy source using massive nuclei. Indeed, fission is only undergone go through for the massive nuclei, or you can say vice versa. The massive nuclei undergo a fission process. The reason is when fission is a splitting of a heavy nucleus into lighter nuclei, and when a massive nucleus breaks into pieces, the binding energy increases. The binding energy increases. An increase in the binding energy per nucleon causes heat release or energy, we should not say heat, energy to release. So if binding energy increase, then then additional energy is released. So only massive nuclei undergoing fission process causes binding energy to increase. That's why it is only suitable for massive nuclei. If you talk about fission in lighter nuclei, so it is not possible. The lighter nuclei only can fuse together in order to increase the binding energy. That's why these two processes are for energy sources. In a nuclear reactor, a uranium-235 nucleus absorbs a neutron and then undergoes fission into two nuclei and some neutrons. So uranium, neutron, rhodium and cadmium. Okay. The fission of complete the nuclear reaction. So we need to find this number and that number. Clearly this is charge. So on the left hand side of the arrow we have total charge of 92, and on the right hand side we have only 48. So here the number should be 92 minus 48, and that number would be equal to 44. And the mass number on the right hand side we have 235 plus 1, 236. So here the number should be 236 minus 111 minus 3, because of this 3. So here number will be 1, 2, 2. The fission of one uranium-235 nucleus is in this reaction releases 3.2 10 to the power minus 11 joule of energy. Calculate the change in mass delta M that occurs in this fission. Quite simple and straightforward question. Energy is given, we need to find mass. So mass energy relation according to Einstein, delta E is equal to delta M C square. So delta M is equal to 3.2 10 to the power minus 11 divided by C square, 9 into 10 to the power 16. So delta M would be equal to 3.6 into 10 to the power minus 28 kilogram. The neutron and product nuclei move away from each other after the fission. A student suggests that this is because of electrostatic repulsion. Comment on this suggestion. So students saying that all the product nuclei and the neutron are moving away due to electrostatic repulsion. No, it is not true. Because neutron is a neutral or uncharged particle, so there is no way, or there is no electrostatic repulsion between the product nuclei and the neutron. They are moving away only because of law of conservation of momentum. Before collision, if you see before a fission reaction, before fission we have a larger nuclei and a small, very small neutron is coming. So we can assume that the initial momentum is approximately 0, or if there is a momentum, it is very small before fission, and then after fission we have a two lighter and the neutron, and they are moving away. The reason is because the initial momentum was approximately 0. In order to conserve momentum, these particles or these fragments have to move away from each other, so that the momentum stays the same before fission and after fission. So there's nothing to do with the electrostatic repulsion. Remember, electrostatic repulsion mean all the particles have same charges. We can consider that because these two nuclei, they have a positive charge, but there's no repulsion between these pieces. But again, these are not moving due to repulsion. They are all of them, all these particles are moving due to law of conservation of momentum. Plutonium-241 is a possible product from a fission reactor. It is a beta emitter with a half-life of 14 years. Calculate the time for 95% of the plutonium-241 in a sample to decay. So how long it takes for a plutonium sample to decay 95%. So you know that you need to find the time. So the idea is n is equal to n naught e to the power minus lambda t. We can figure out this t. and they are saying that the only this n is a number of atoms that stays or remains in time t. So basically, don't confuse with this 95%, particles have decayed, only 5% left. So n is 5% of n naught is equal to n naught. So n naught is gone. Again, I am not moving forward because we know that we don't have lambda to find the t. That means in order to move on to find t, we need first lambda. So for lambda, we are given half-life. So we can find lambda. Lambda is decay constant. So you know that since lambda, which is decay constant, is equal to ln2 divided by half-life, t half. So ln2 divided by 14. So decay constant would be 0.0495 per year inverse per year. This is decay constant. And now use this lambda here. So you have a 5% number on the left hand side. So 0.05 is equal to e to the power minus lambda. Lambda is a 0.0495 into t. Take log on both sides, taking ln. So if you take ln, then answer would be equal to minus 2.995 is equal to, and this e gone, so minus 0.0495 into t. And now you can find t, dividing and cancelling negative, so t would be equal to 60.5 year. When a ship is sailing on a rough sea, the waves can set the ship into simple harmonic motion. This can result in passengers becoming seasick. State what is meant by simple harmonic motion. A typical definition of simple harmonic motion. So simple harmonic motion, SHM, and the motion in which acceleration is directly proportional to the displacement from the mean position and always acts towards the mean towards the equilibrium position. So this is the mathematical form of simple harmonic motion. You can use acceleration, or you can say force acting on the particle is directly proportional to the displacement from the equilibrium position and always acts towards the equilibrium position. So you can use any of these two definitions for simple harmonic. At one position on a ship, passenger experience vertical oscillation of amplitude 0.85 meter with a period of 6 seconds. Calculate maximum acceleration of the passenger. So we are given a period which is capital T, and this is the amplitude x, you can say, or x naught, whatever. And then we need to find acceleration. So if you see simple harmonic motion acceleration is generally v square over r, or you can say v is a linear velocity, but we are not given linear, so let's convert this into angular velocity. So v is equal to r omega, or r is the amplitude, so x naught omega square over this r is x naught, or even you can use r, it's your choice. So one x naught gone here, so finally a equal to x naught omega square. And how do you find omega? Omega is 2 pi by t. T is the period. So if you find omega omega would be equal to 2 pi by t. 2 pi divided by t, t is 6. So your answer will be 1.05 radian per second. And then you substitute this value in here. So acceleration is equal to x naught, which is the amplitude, 0.85 times omega square, so 1.05 whole square. So a would be equal to 0.937 or 94 meter second minus 2. This is the acceleration. Passengers on a ship may suffer from seasickness as the ship rises and falls on the wave. The graph shows the limits of passengers' tolerance to the oscillatory motion. So we have a graph of period of motions and acceleration divided by acceleration due to gravity. So this is the ratio of acceleration in the motion with the acceleration due to gravity, and these are different regions. So not noticeable, tolerable, uncomfortable, and intolerable. So determine whether the passengers are likely to feel seasick as a result of ship's motion. You should use your value from BI or B1 and show how you have used the graph. So what do? We have already found acceleration in BI. Since acceleration we found is 0.94 meter second minus 2. So we just find that number. So A by G will give us 0.095, and we know that also if you read the question, t was given 6 seconds. So 0.095, that means approximately 0.1. So 0.1 slightly lower, and the 6 time period is 6, and we have here. Now you see we have tolerable region. So you can say that now the motion of the ship will be tolerable. So you write the comments that the motion of the ship is tolerable. It will be good if you mention that point here. The graph shows how the vertical displacement x of a passenger varies with time t. Add to the graph to show how the acceleration of the passenger varies over the same time interval. Okay, so we are given position time graph, and we need to plot acceleration graph. And if you see, the position time graph obeys cosine law, and you know that since x is equal to x naught cos omega t, this is the relation between position and the time, and that's why we have this graph. And we also know that velocity graph will be x naught omega sine omega t with negative sign, and acceleration is negative x naught omega square cos omega t. So if you see position time graph follows cosine law, and acceleration also follow cos graph, but with negative direction. So you can start your graph from here, and it should be a cos graph, something like this is acceleration time graph. A passenger on the ship stands on weighing scale when the sea is calm. The reading on the weighing scale is 75 kg. Okay, draw free body diagram for this passenger. So it's straightforward. Sea is calm, no other weight except no other force except the weight acting down and contact force acting upward, and both are equal. Reading is 75 kg. On a rough sea, the ship oscillates vertically with a large amplitude. Explain why the reading on the weighing scales will vary. Indeed, when the sea is on a rough sea, we have oscillatory motion uh, in the sea or in the passenger, and this oscillation causes additional force acting on the system. So this additional force varies with the amplitude. As amplitude keep varying, the force keep changing, and also the direction keep changing. So other than weight and the contact force on the passenger, we have additional force F, additional force acting on the passenger, and this F keeps changing in magnitude, keeps changing in terms of magnitude as well as direction. It depends on the position of the ship at that moment, where ship is going up over the wave or going down through the trough of the wave or something. So because F is changing, so that's why the R contact force keeps changing. So if ship is at the higher peak of the surface here, then at that moment R will be less than W. If R is less than W, then the reading on the scale will decrease. Or if the ship is at the lower point, then R will be greater than W, so it will read the higher value. So reading increase. Whilst the passenger is standing on the weighing scale, the maximum acceleration of the ship is 0.7 meter per second square. Calculate the maximum reading on the weighing scale. So they are talking about maximum acceleration and calculate the maximum reading. So maximum reading means R is maximum, R is greater than W. That means it is, at the bottom of the wave, and that means at that moment the resistance force, the sorry, not resistance, resultant force. At that moment, resultant force R minus W would be equal to MA. So R is equal to MA plus mg, and you substitute the value. So 75 times of acceleration, 0.7 plus 75, which is mass. If you see the previous part, 75 is given, g is 9.81. So R would be equal to 78.8.5 Newton, and this is the weight. So the reading on this is the weight, or Newton acting, and the mass would be equal to 788.5 divided by 9.81. So the answer will be equal to 80.35 kilogram. That's what the reading will be showing. So 80. Thank you very much. I hope you understand. See you in the next video. Have a nice time.